Hello students, in today's class we are going to learn the next part of chemical bonding, that is valence bond theory. As we know that the Lewis approach helps us in writing the structure of molecules, but at the same time it fails to explain the formation of a chemical bond. It also does not give any reason for the difference in bond dissociation enthalpies and bond lengths in molecules such as hydrogen and that of fluorine. You can see that both of them will be formed by single covalent bond by sharing of electron pair between the respective atoms. But the bond enthalpy of hydrogen is 435.8 kilojoules per mole and that of fluorine is 155 kilojoules per mole. Whereas bond length of hydrogen is only 74 picometer, but that of fluorine is 144 picometer, right? So therefore valence bond theory will be having an explanation with respect to bond dissociation enthalpies and even bond length also. And if you see the Lewis theory, the drawback of Lewis theory is that it gives no idea about the shape of polyatomic molecules. It reveals that valence bond theory is able to explain the shape of polyatomic molecules. The valence bond theory was proposed for the first time by Hitler and London to explain the formation of a covalent bond quantitatively. And the main postulates of this theory are, the first one you can see that a covalent bond is formed by overlapping of two half-filled valence atomic orbitals of the two atoms. Let me take the example of a formation of a hydrogen molecule. So hydrogen molecule, two atoms are there of hydrogen. So let me write the orbital of one hydrogen and another orbital of another hydrogen atom. So we can see that it will be having one electron and this will be having another electron with opposite spin. And if at all if a molecule of hydrogen has to be formed, so there will be overlapping of the two half-filled atomic orbitals, and these two electrons will be forming one pair of electron, and thus we call it as overlapping has been formed, right? So the second postulate, if you see, the electrons in the overlapping orbitals get paired and are confined between the nuclei of the two atoms, right? The third point is that electron density between the two bonded atom, it goes on increases due to the overlapping. Thus this confirms the stability of the molecule. The greater the extent of overlapping, stronger will be the bond formed. And the last point is that the direction of the covalent bond is along the region of overlapping of atomic orbitals. It reveals that the covalent bond is directional, whereas ionic bond is non-directional. The valence bond theory, which is abbreviated as VBT, was further developed by Pauling and others by introducing the concept of hybridization, right? So we have already learned this definition in the case of unit 2, that is mixing up of two or more atomic orbitals of slightly different energy to give new orbitals of equivalent energy. The phenomena is called as hybridization, and the new orbitals obtained are called as hybrid orbitals, right? Discussion of this VBT is based on the knowledge of atomic orbitals and electronic configuration of elements. Very important point which you have learnt in unit 2. The overlapping criteria of atomic orbitals, the hybridization of atomic orbitals, and the principles of superimposition are very important to understand valence bond theory. So it is very important for us to know the different types of orbitals and all, right? So in this slide we are having the s orbital, so I will write here a, which is nothing but it reveals about s orbital, and here I will write it as b, which is p orbital, and this is a c, where all the p orbitals are there with respect to their axis, and this is d, and this is e, where d and e are nothing but the d orbitals only, but images are same, but their position is different, right? So let us try to understand with respect to this a, that is s orbital. So whenever I say s orbital, one has to understand that it is a spherical in a nature, right? So these are the coordinates, which we call it as x-axis, this is y-axis, and this is z-axis, right? And it has been mentioned here 2s. It can be either 1s or 2s or 3s. Altogether, in the sense, we can say that s orbitals are always spherical in nature. Now coming back to this other part, that is called as what a p orbital, which we can see here, right? So p orbital, there are totally 3 p orbitals. One is along x-axis, right? One is along x-axis, and other one is along y-axis, and other one is along the z-axis, right? I hope you are able to see this. So one is along x-axis in the sense the orbital is present in the x-axis. So this is what the x-axis, which is having what the orbital. Similarly, if I say that is like y, right? So you can say that this is the orbital which is present in the direction of what y, and that of z-axis, you can see that this is the p orbital that is present along the z-axis. One has to recall that the capacity of each orbital is what 2 electrons, right? So in general, if I say that there are p orbitals, so there are 3 p orbitals, and the total capacity of the orbital is 6 electron. Is it clear, students? In this picture you can see that we are having all the p orbitals. One is along x-axis, other one is along y-axis, and the other one is along z-axis. In the next part, if you see here, there are d orbitals. Total d orbitals are 5 d orbitals, right? For our sake of convenience, we write these orbitals in terms of what 5 orbitals, right? Like this we write. And as I've already told you that each orbital capacity is of what 2 electrons. So therefore, if I write all these orbitals having what total number of electrons, so the total capacity of these orbitals will be what 10 electrons, right? So these 5 orbitals, let us have the discussion of these 5 orbitals. The first one I call it as dxy, right? And after that I want to go with respect to dyz and dxz and dz square, and here this is dx square minus y square. If you see this dxy, right? So here you can see clearly that it reveals that the orbitals are present between x and that of y. So here this is x and here this is y axis. So this is the lobe that is present here, x between x axis and between y axis. Similarly, the other lobe is present here. I hope you are understanding, students, right? So this is the dxy orbital. And if you see with that of dyz orbital, it means that the orbital is present between the y-axis and the z-axis, right? So this is the y-axis here and this is the z-axis, right? So the orbitals are present between y and that of what z. So this is one of the lobe that is present between y and z. Similarly, this is the other lobe which is present between y and z. The next one is with respect to dxz. So this is x, this is z, right? So you have to just correlate that the orbital is present between x and z. So if you see, this is the orbital that is present between that of x and that of z. So it is present in this manner here, and the other lobe that is present between the x and the z axis, right? The next one is dz square. It means that the lobe is present along the z axis, right? So this is the d orbital which is present along z axis, and it is usually represented as dz square, right? And the last one, which is simply called as dx square minus y square. It means that the lobe is along the axis, that we have to remember here. Okay, this is x, right? And the other one is along with that of the y axis. We call it as x square minus y square. Remember students, the two orbitals which are present along the axis are, one is dz square, other one is dx square minus y square. But whereas remaining, that is dxy and dyz, and the last one is that is dxz. Here the lobes are present between the axis. The same d orbitals, if you see in another picture here, if I say with respect to dxy, right? So if I say with respect to dxy, right? So you can see that this is the plane here. The plane here, that is dxy, right? So this is the plane here which is available with us, right? And if you see the orbitals, these are present between x axis and y axis, right? So these are the orbitals which are present along the axis, that is between the axis, right? xy. Similarly, if you see for yz, that is a dyz orbital, so this is the plane, we can see that it is present here, and the orbitals that are present between y axis and that of z axis, right? So if you see here, this is the orbital that is present between y and z. The next one is with respect to x and z. So this is the plane which will be carrying the orbitals, right? So as I've already mentioned that the orbitals should be present between x and that of z, right? So the orbitals, we can see that this is the orbital which is present between x and z, and this is the another orbital which is present between the x and z axis. And coming back to the last one, that is a dx square minus y square. It means these are the orbitals which are lying along the axis. This is x square, and the other one which is nothing but called as y square. And the last one, that is the fifth one, that is dz square, where the orbital is present along the axis. A rigorous treatment of valence bond theory in terms of these aspects is beyond the scope of our NCERT textbook. Therefore, for the sake of convenience, valence bond theory has been discussed only in terms of qualitative terms but not quantitative terms. To start with, let us consider the formation of a hydrogen molecule, which is the simplest of all the molecules. Let us consider two hydrogen atoms A and B which are approaching to each other, having nuclei Na. It means the nuclei that is associated with the hydrogen atom A, and N of B, which means the nuclei is associated with the hydrogen atom B, and the electrons present in them are represented by E of A, and other one is E of B, right? When the two atoms are at large distance from each other, there is no interaction between them. As these two atoms approach each other, new attractive and repulsive forces begin to operate. I repeat it once again. When the two atoms approach each other, there are two types of forces. One is attractive forces and the other one is repulsive forces begin to operate. Let us try to understand with the diagram. In this diagram, you can see that first of all I want to go with this point, that is attractive forces tend to bring the two atoms close to each other, whereas repulsive forces tend to push them apart, which is shown in the figure, that is a 4.7, which is also present in our NCERT textbook. The same thing has been retrieved. Now in this diagram I want to concentrate on this part, that is attractive forces. Right, later we'll be discussing with respect to the repulsive forces. As I have already explained that there is an hydrogen atom called as H and it is represented as A. Similarly, there is another hydrogen atom H which is represented as B. This is the nucleus of this hydrogen atom and this is the nucleus of this hydrogen atom. Right, now let us try to concentrate on the old and new forces. Here old forces are represented by dashed line, but whereas the new forces are represented by the complete line. Right, so electron of this HA, which I want to write it as E of A here. Right, so it has been mentioned with respect to dotted line. So this is the old forces. It means that this electron E of A is belonging to this hydrogen atom, and this is the old force. Right, this is nothing but called as water. I want to represent it by dotted line, so this is called as old forces. Right, similarly we can see that this hydrogen atom which is called as H of B is having the electron which is called as E of B, which is present here, and the operating forces which are nothing but what, attractive forces, but these are old forces. Right, but if you see exactly this what is this hydrogen atom will tend to attract the electron of other hydrogen atom, that is E of B. So therefore these forces are nothing but what, new forces. Right, similarly the electron E of A will be attracting towards the hydrogen atom H of B, which is again called as what, new forces of attraction. Right, and at the same time we have to concentrate on repulsive forces operating. So these repulsive forces, if you see here, this is the positively charged nucleus. Okay, and even this is also positively charged nucleus. So this nucleus and this nucleus which are having positive charge, they tend to repel. So that repulsive forces are given here. H of A is repelling with respect to H of B, and at the same time the electron E of A will be showing repulsive forces with respect to E of A, and that is shown in this direction in the other diagram. I hope you have understood the attractive forces and the repulsive forces. Now experimentally it has been found that the magnitude of new attractive forces, I want to repeat the term, that is magnitude of new attractive forces is more than the new repulsive forces of interaction. Thus, as a result, when the two atoms approach each other, their potential energy will be decreasing. Ultimately, a stage is reached where the net force of attraction balances the force of repulsion and the system acquires minimum energy. When the system is acquiring minimum energy, we can say that stability has been reached. At this stage, the two hydrogen atoms are said to be bonded together to form a stable molecule having a bond length of 74 picometer, which has been determined experimentally. In this diagram we can concentrate on the particular diagram here, that is on x-axis we can see that internuclear distance is present, and on y-axis we can see that energy which is present in kilojoules per mole, which has been mentioned over there. Right, so this is the energy which has been mentioned in terms of kilojoules. Right, and here there is what the point which is mentioned as 0. It means that above this the energy is positive and below the energy is what, negative. Right, so we can see that here there are two hydrogen atoms which are far from each other, but this is called as a distance of separation, right? When we move towards this part here, it means that the hydrogen atoms are coming closer. When they are coming closer, their energy will be decreasing, right? Similarly, at this point, that is when they are very close with each other, there results a formation of overlapping here. At this part, we can say that this is the energy difference between the two hydrogen atoms, which we call it as what? A bond energy. It means that when they overlap, the energy that is present between the atoms of these two, which is called as bond energy, and that distance we call it as bond length, which is 74 picometer. Apart from that, if they still overlap, then they will be having excess energy. It means that the curve will be what? Rising, and that we can see here, that is positive, right? So therefore this energy is called as what? A bond energy, and this distance is called as a bond length, right? So in figure 4.8 in our NCERT textbook, we can see that the potential energy curve for the formation of a hydrogen molecule as a function of internuclear distance of the hydrogen atoms, right? The minimum in the curve, that is nothing but this part. This part is nothing but called as what? Minimum, right? The minimum in the curve corresponds to the most stable state of the hydrogen. Is it clear, students? And now we have to concentrate that whenever this molecule, hydrogen molecule, has been formed, their energy gets what? Released. When the bond is formed between two hydrogen atoms, the hydrogen molecule is much more stable than that of the isolated hydrogen atoms. Earlier we can see that these were the two isolated hydrogen atoms, but when the molecule has been formed, energy will be what? Liberated. This energy, or the energy so released, is called as bond enthalpy, which is corresponding to the minimum in the curve depicted in figure 4.8. and at the same time, conversely, I want to say that this 435.8 kilojoules of energy is required to dissociate 1 mole of hydrogen molecule. It means that if I want to break that hydrogen molecule, that much of energy is required to dissociate 1 molecule of hydrogen molecule. Now we are going to learn about orbital overlap concept. In the formation of a hydrogen molecule, there is a minimum energy state when the two hydrogen atoms are so near that their atomic orbitals undergo partial interpenetration. So if I just want to represent this diagram here, okay, that is nothing but called as partial interpenetration. So this is overlapping, right? So this partial merging of atomic orbitals is called as overlapping of atomic orbitals, which results in a pairing of electrons. The extent of this overlap decides the strength of this covalent bond formed, and in general, greater the overlap, stronger is the bond formed between the two atoms. Therefore, according to this orbital overlap concept, formation of covalent bond between the two atoms results by pairing of electrons present where in the valence shell having opposite spins. That is very, very important. Now we are going to learn about some directional properties of the bonds. The meaning of covalent bonds being directional is that atoms bonded covalently, they prefer some specific orientations where in space relative to one another. As a result, molecules in which atoms are bonded covalently have definite shapes. This point is very, very important, students. Is it clear? That is, whenever a covalent molecule is formed, they will be having some directional properties, and that directional property is nothing but what? The bonded atoms will be preferring specific orientations. As we have already seen, the covalent bond is formed by overlapping of atomic orbitals, right? For example, the molecule of hydrogen is formed. How it is formed? Due to the overlap of 1s orbitals of two hydrogen atoms. But whereas in the case of polyatomic molecules in which there are more than 2 or 3 atoms, such type of molecules we call them as polyatomic molecules, such as CH4, which is called as methane, NH3 we call it as ammonia, and H2O, which is nothing but a simple polyatomic molecule, that is water, right? The geometry of the molecules is also important in addition to the bond formation. So we have to learn about the term called as what geometry. In the next slide we'll come to the conclusion with respect to what geometry and all, right? Now, for example, why it is so that this CH4, that is called as methane molecule, is tetrahedral in shape, and the bond angle between the hydrogen, carbon and hydrogen, that is nothing but the bond angle, okay, that bond angle is 109.5 degrees. So this angle, why it is 109.5 degrees, and this is shape which we simply call it as what a tetrahedral shape it is, okay. So this we call it as tetrahedral shape. Why similarly, why the shape of NH3 molecule is pyramidal in nature? So you can see that this NH3 nitrogen here and the 3 hydrogen atoms are present here, okay. So what does this mean? This bond is present behind the plane of paper, and this bond is projecting towards the observer in the plane, and these are the 2 bonds which are present in the plane. So these are 3-dimensional structures. So here we have to concentrate that why the shape of NH3 molecule is pyramidal. So this pyramidal nature, that shape of pyramidal of with respect to this NH3 molecule, or that of the tetrahedral shape with respect to this methane molecule, the valence bond theory explains the shape and the formation and directional properties of this bonds in polyatomic molecules like methane, ammonia and water, etc., in terms of overlap and hybridization of atomic orbitals. Now let us try to understand overlapping of atomic orbitals, right? So when orbitals of 2 atoms come close to form a bond, I repeat it once again, when orbitals of 2 atoms come close to form a bond, their overlap may be positive, or it might be negative, or it might be 0, depending upon the sign phase. This is very important, okay. Now here sign doesn't mean with respect to the charge, that I want to mention here, that sign is not with respect to charge. It represents that the orbital, whether it is having same sign or not, that is very important, right? And the direction of orientation. So this is very important point, direction of orientation of amplitude of the orbital wave function in space. In the next slide I have been made it very clearly, so you'll be understanding, okay. So this part of diagram is a little bit of explanation. The same diagram I have taken into the next part of the slide where you can understand it very clearly, right? So next point is that the positive and negative sign on the boundary surface diagram in the figure 4.9 in our NCERT textbook, which has been mentioned over there, show the sign phase of orbital wave function. This is very important, orbital wave function, and are not related with the charge, right? Orbitals of forming bond, I repeat it once again, orbitals of forming bond should have same sign, which is called as what a phase, and their orientation in space. This is called as positive overlap. Various overlaps of s and p orbitals are depicted in figure 4.9. It means that in the present context we are going to concentrate on overlapping of s and p orbitals, right? So here you can see that a positive or in phase overlap and here you can see that negative or out of phase of water overlap. Now, as I told you that we'll be discussing in detail, so this is a slide present here where we can see the positive or in phase overlap, and similarly here you can see the negative or out of phase overlap, right? And in all of these pictures you can see that Z has been mentioned. It means that Z is taken as intermolecular axis. Z is taken as intermolecular axis, right, students? Now let us consider the first one in the case of a positive or in phase overlap, right? So here you can see that along the Z axis there is one orbital which is called as PZ, right? So here it is having the positive sign. It means that it is having electron density there. Similarly, if a positive overlap has to be formed by another PZ orbital, it means that that orbital should be also having the positive electron density. Then only we can call it as positive or in phase overlap, right? So at the same time, if you see the negative or out of phase overlap in this diagram, we can see here that the positive sign, that is simply called as electron density, is here with respect to one PZ orbital, and the other one which is having the negative part which is called as out of a phase. So there won't be the formation of bond here. Concept is clear, students? So this was all with respect to PZ and PZ positive. PZ and PZ where there is a negative or out of phase overlap. Similarly, if a PZ orbital is overlapping with a S orbital, then at the same time there should be a positive sign, that is with respect to electron density. So therefore this is the overlapping part here. So then only it is called as positive overlap. And at the same time, if you see the negative, PZ orbital is here which is overlapping with the S orbital, but it is negative overlap because it is having a negative sign, and here it is having a positive sign. It reveals that the electron density is not there with respect to PZ orbital. Is it clear, students? In the next example, that is with respect to this part C, here there are px orbital. So this is the p orbital which is along a x-axis. Similarly, there is another p orbital which is along x-axis, but they are forming a positive overlap. It means that both are having the same sign, that is nothing but electron density positive. So therefore here I can say that there is a positive overlap. Now we'll move towards the negative overlap here with respect to this G here, right? So here there is a px orbital, here also there is a px orbital, but you can see that one px orbital is having positive sign, other one is having negative sign. It means that overlapping is possible, but it is which type of overlap? Negative overlap is there. It means that the bond is not formed there. Similarly, in the positive overlap with respect to this example D, there is an orbital which is called as p orbital, but it is in y-axis. Similarly, there is another p orbital in y-axis, but both are having a positive sign, that is electron density. They are going to overlap, which is called as positive overlap. But in the case of this example H, the py orbitals are overlapping, but the overlap is called as a negative overlap because the two orbitals are not having same sign. I hope you understood what is the meaning of positive overlap or in phase overlap, or that of negative overlap or out of a phase overlap. Is it clear, students? Now let us have with respect to this another term called as zero overlap, out of a phase due to different orientation and direction of approach. Is it clear, students? So in this one example here, we are having one orbital which is called as p orbital, and that is along x-axis, right? Another orbital is there, that is with respect to s orbital, so it is approaching in this manner. So here there is no overlap, which we call it as zero overlap. If at all, if a bond has to be formed with respect to px and that of ps, this s should have been present here, right? So that positive and that positive would have been form a bond here. Is it clear, students? And if you take that of what here another part, that is what J here, we are having one p orbital, that is px orbital, other one is what a py orbital. So different orientation and direction of approach is different, which we call it as out of phase, and that leads to what a zero overlap. The criteria of overlap as the main factor for the formation of a covalent bond applies uniformly to the homo-nuclear. Homo-nuclear means just like what H2 or that of what N2, which are called as homo-nuclear molecules, diatomic molecules, or that of a hetero-nuclear diatomic molecules and polyatomic molecules. We know that the shape of methane, ammonia and water molecules are tetrahedral, pyramidal and bent respectively. This statement I do understand, but I have to make you explain why the methane is having tetrahedral shape, why the ammonia is having pyramidal, or that of water is having what bent shape, using what a VBT, that is valence bond theory. It would be therefore interesting to use this valence bond theory to find out if these geometrical shapes can be explained in terms of what orbital overlaps. This part we are going to learn in the next class. Thank you so much.